Welcome to today's Explainer. We're jumping right in today because we're investigating what I honestly like to call the ultimate cosmic crime scene, the universe's absolutely glaring lack of antimatter. I mean, it's easily one of the most profound mysteries in all of physics, and to solve it, we really have to look at the very foundation of reality itself. Okay, let's dive into this. Just look around you for a second. The entire visible universe is composed of matter particles, right? Protons, neutrons, electrons. You definitely don't see their antimatter partners, like antiprotons, antineutrons, and positrons, just hanging around your living room. But here's the kicker. According to the fundamental laws of physics, the Big Bang should have created exactly equal amounts of both, a perfect 50-50 split. So why is there so much of one and literally none of the other? Here is our quick roadmap to figure this out. 1. The Antimatter Mystery. 2. Sakharov's 3 cosmic rules. 3. The mirror smashed, CP violation. 4. Is electroweak baryogenesis dead? 5. The leptogenesis alternative. And 6. The LHC's ongoing search. Section 1. The Antimatter Mystery. Let's start right at the heart of our crime scene. Think about this. If the universe actually started with perfectly equal densities of matter and antimatter, we wouldn't even be here. Seriously. Without some sort of fundamental imbalance being introduced super early on, those equal amounts of matter and antimatter would have just found each other, paired up, and completely annihilated one another. The whole universe would just be a totally empty sea of radiation. Just to make sure we're on the same page, antimatter is not just a sci-fi trope. It is perfectly real. An antimatter particle has the exact same mass as its standard matter counterpart. The difference? Its additive quantum numbers, most notably its electric charge, are completely reversed. They are, for all intents and purposes, perfect opposite twins. Section 2. Sakharov's 3 cosmic rules. So how did regular Mar win this cosmic war? Back in 1967, brilliant physicist Andrei Sakharov laid out the absolute rules of the game for this to happen. He figured out that 3 specific conditions had to be met. First, the proton must be unstable, allowing for what we call baryon or lepton number violation. Second, there absolutely must be interactions that violate C, which is charge, and CP, charge parity symmetries. And third, the universe had to undergo extremely rapid expansion to stop all that matter and antimatter from just pairing back up. So the crucial point is, any theoretical suspect we evaluate to solve our mystery has to check every single one of these boxes. And this checklist is literally the only way we exist. If a theoretical model can satisfy these 3 strict rules, it can successfully explain how an initial perfectly equal split of matter and antimatter mathematically evolved into the matter-dominated universe you and I are currently standing in. Section 3. The mirror smashed. CP violation. This brings us to the biggest clue at our crime scene. Let's unpack CP symmetry really quick. The C stands for charge conjugation. That basically means swapping a particle with its antimatter counterpart. The P is for parity, which is essentially a spatial mirror image. You take coordinates x, y, and z, and you just flip them to -x, -y, and -z. For a really long time, physicists were convinced the universe was perfectly symmetric under these transformations. To really visualize this, we need to introduce particle spin, specifically something known as helicity. Think of it like a screw. A positive helicity particle is like a right-handed screw. Its spin lines up perfectly with its velocity. A negative helicity particle is left-handed, so its spin is anti-parallel to its velocity. When you apply a parity transformation, that spatial mirror image we just talked about, the velocity direction is reversed, but the internal spin direction isn't. Therefore, a positive helicity particle flips directly to a negative one. And here comes the grand plot twist in 20th century physics. Right up until 1956, parity was just assumed to be universally conserved, period. But then Li and Yang proposed, hey, maybe it's not. Literally just 1 year later, Xian-Shung Wu completely shattered that assumption by proving through beta decay that electrons were predominantly left-handed. Then, in 1964, Cronin and Fitch found this tiny anomaly in the decay of neutral kaons. They discovered that CP symmetry wasn't absolute either. It was violated. Now, under a perfect CP transformation, a negative helicity proton is supposed to perfectly become a positive helicity antiproton. But those tiny anomalies found by Cronin and Fitch, they proved this perfect mirror is actually cracked. Nature does in fact treat matter and antimatter slightly differently, completely fulfilling Sakharov's second rule. Section 4. Is electroweak baryogenesis dead? Let's check out our prime suspects. So with CP violation confirmed, physicists went to work building models. One heavily debated suspect is electroweak baryogenesis. It's incredibly appealing, mostly because it relies on physics at a scale we can actually test in our particle colliders right now. But is it already a dead end? Like this paper from James M. Klein asks, have our colliders completely ruled it out? And this brilliantly illustrates the drama of the ongoing scientific debate. Older frameworks of this theory are totally failing. The minimal supersymmetric standard model, that required light top squarks, but the Large Hadron Collider data has officially ruled those out. 2 Higgs doubled models, they require such massive, unnatural fine-tuning they literally hit mathematical dead ends known as Landau poles. But check out that bottom row. Models introducing a scalar singlet remain highly viable. They allow for a strong phase transition without all that messy fine-tuning. In fact, Klein points out something super clever. By adding a neutral Majorana fermion to that scalar singlet, you don't just dodge the LHC's current exclusions. Actually, you create a brand new source of CP violation that is directly linked to dark matter. This suspect cleverly uses dark matter interactions to generate that baryon asymmetry we've been hunting for. Section 5. The leptogenesis alternative. But wait, we have a competing theory. Enter leptogenesis. It's currently the favored paradigm for a lot of physicists. The real beauty of leptogenesis is that it comes almost for free if you simply invoke the seesaw mechanism, which is already used to explain why neutrino masses are so incredibly tiny. In this model, heavy Mariana neutrinos decay, generating an asymmetry in leptons. Then, later in the universe's evolution, these crazy phenomena called sphellaron processes act as a cosmic crucible, directly converting that lepton asymmetry into our matter-dominating baryon asymmetry. But there is a massive catch. Leptogenesis relies on physics at the unimaginably high energy scale of heavy neutrinos. We're talking roughly 10 to the 10th power giga-electron volts. Unlike electroweak baryogenesis, which we can poke and prod right now, leptogenesis requires energy levels so extreme that we might literally never be able to experimentally verify it. It's an elegant suspect for sure, but one that completely refuses to sit in the interrogation room. Section 6. The LHC's ongoing search. Let's look at the actual detective work happening today. Now, what's really interesting about this slide is just how rapidly our experimental evidence is accelerating. It took literally decades after the 1960s to finally detect direct CP violation in K-mesons back in 1999. Then, fast forward to 2019, the Large Hadron Collider's B experiment observed it in the D0 meson. And zooming right up to July 2025, they've just observed CP violation in a baryon for the very first time, specifically the beauty lambda baryon, which is made of an up, a down, and a beauty quark. And why is that recent discovery such a big deal? 5.2. That is the exact number of standard deviations by which the beauty lambda baryon decay differs from 0. In the incredibly strict world of particle physics, passing that 5 standard deviation threshold is the absolute gold standard. It officially confirms the observation of CP violation in this particle. We are continually, relentlessly finding new cracks in the cosmic mirror. Which leaves us with a final, pretty staggering thought. We know C and P symmetries are broken. We know their combination, CP symmetry, is definitely broken. But what about CPT symmetry? This is the ultimate discrete symmetry. It states that a mirror image antimatter universe with time running entirely backwards should look completely identical to ours. Physicists are really holding out hope that this ultimate symmetry holds true. But as we continue to unlock these wild secrets of antimatter, we have to wonder, is time itself the next mirror to shatter?